Now with that, I'd like to invite Dr. Cooper to turn her camera on. I'm going to do an introduction now for her as our opening keynote for Beyond the Cradle 2021. We're so delighted that she's with us. Dr. Cooper is the Planetary Protection Lead for NASA's JPL Perseverance rover, also known as the Mars 2020 mission. She's also contributed her expertise to the InSight mission and the upcoming Europa Lander mission. In these endeavors, she carries out the critical planning and guides the technical design work to make sure we're not carrying our own microbes with us on the way to Mars, and that we can have faith in the rigor of astrobiology results that may come in through, in this case, the rover's payloads in the case of Perseverance. Dr. Cooper holds a BA in physics, a master's and PhD in mechanical engineering, where her dissertation studies involved non-equilibrium plasma sterilization of spacecraft materials. Dr. Cooper is an accomplished and avid public speaker and has received several awards for her work at NASA, including the NASA Early Career Public Achievement Medal, the Charles Alachi Award for Exceptional Early Career Achievement, and a NASA Group Achievement Award for exceptional performance in the rigorous evaluation and rapid synthesis of a development strategy for the Mars Sample Return Planetary Protection technology. With that, Dr. Cooper, we are delighted and honored to have you with us today, and I'd like to pass the Zoom baton to you for your presentation.
Awesome. Thank you so much for that kind introduction. It is such an honor to be here and to talk to you about planetary protection in the context of the Mars 2020 mission. And I hope you see the parallels in envisioning a new space age and carrying planetary protection with you in your quiver of tools. So I will now share my screen and share my presentation here. So today I will be talking to you about Mars 2020, and by the end of this lecture, I hope that you will all be deputy planetary protection engineers and really just carry the understanding of what planetary protection is, why it's important, and build it into your designs and how you implement missions that you'll be working on in the future. So just to set the stage, just to take a step back for a second, if you look at life on Earth, the oldest form of life that is present here on our planet is in the form of microbial life. And microbial life is quite interesting. They are found in various environments, to include very harsh environments. If you look in the desert, there was a time where in Death Valley and all of these very harsh environments, the scientists thought that life maybe didn't exist there. It was too harsh for it to exist. And over time, with the development of more sensitive detection capabilities, we were able to see, yes, there are indeed microbes that survive in these harsh environments, whether it be high temperature, low pH, high heavy metal content. It is amazing how resilient these microbial life that we can find here on Earth are. And when you also look around at the environments that they're in, you can also see that they have an environmental and ecological impact. If you look within your own ecological system, your body, you can see that microbes, I'm sure every single person listening to this seminar has had food poisoning. And so you have direct experience of an ecological impact of microbial life. And so you would envision, okay, if they have such a large impact on an environment, you could extrapolate that if you look at space exploration, that you would really want to be concerned with understanding what microbial life may be transported on your spacecraft and possibly limit that amount, especially if you're going to a place that may have life at that destination. And so that's kind of the fundamental basis of planetary protection. And I'll talk a little bit more about that and how it's implemented specifically. But so planetary protection kind of varies. What you do to your spacecraft depends on where you're going. So if you are, for example, sending a mission to the sun, if you are going to orbit the sun, or if you're going to eventually have an end of life in the sun, we know the sun does not have any form of life. And so there are less restrictions and requirements on a mission that's going to a place that we know does not harbor life. If, for example, you're going to Europa, we know has oceans under that very thick layer of ice. And with that potential of life potentially existing there, that completely changes the game. And there are more stringent requirements that are applied to the spacecraft because you're going to a place that may harbor life. It also depends if you are, for example, going to a place where we know life doesn't exist, but you're going by way, your orbital path goes by way of a place that we do suspect life exists, and you may have a chance to impact that area, then a hybrid set of requirements get applied to your mission. So it really depends on where you're going, that the level of stringency that's applied. It also depends on what you're doing. If you're flying by, there's a set of requirements, and it completely varies from if you're roving on the surface of a planet or a moon or a different body in our solar system. So with that combination of knowledge of what you're doing, where you're going, and what type of science you're doing, then a planetary protection mission categorization is applied to your spacecraft. And based on that, all the way from the design to the build and launch, through launch, a set of requirements are applied to your spacecraft. So now let's focus in on the Mars 2020 mission. We know that it is a mission to Mars. It is a rover. On the left side of your screen, you can see just a video that I took. If you go to mars.nasa.gov/Mars 2020, you're able to actually interrogate every single instrument, every single subsystem, the mobility system, the belly pan, all of those parts. You can click on it and find out more information about each component. So this rover has landed on the surface of Mars. It has its sidekick, Ingenuity. And I'll talk a little bit more about that toward the end of this lecture. But it is roving on the surface. It is landing in Jezero Crater. So here is a map on your right side here, a map of Mars, and it shows the landing site, Jezero Crater, with respect to all of the other rovers and landers that successfully landed on the surface of Mars. And Jezero Crater is a key location for landing because several million years ago, 3.5 to 4 billion years ago, it used to look like what you see in front of you, this ancient lake with a nice inlet of water flowing in. And if you fast forward to today, this is what it looks like today. So you can see the river delta here of where the water is coming in and all of the sediments and really interesting features that it created. And if you were to go and find your nearest lake in your backyard or in your neighborhood, and if you were to take a scoop of sediment from the bottom of this lake and put it under a microscope, you would see a large quantity and diversity of microbial life. So if you want to set yourself up for success to find signs of ancient microbial life on Mars, this is the perfect place to go. So that is one of the main reasons why Jezero Crater was selected as a landing site. And the purpose of this mission, there are several science goals, to understand, first of all, whether or not life ever arose on Mars, so to look for these ancient signs of microbial life. And you'll actually hear a fantastic talk by Dr. Rohit Bhartia later on in this series, where he'll talk about Sherlock, his instruments. And so I won't take away his thunder, but there are a lot of great developments on the science instrument side to meet that goal. Also, the next goal is to look at the climate of Mars and characterize the climate of Mars. And we have various instruments, to include META, that will take various instruments and look at the radiation profile, to look at the wind intensity and direction, and really allow us to understand the Martian climate. We're also meant to characterize the geology on Mars, as well as prepare for human exploration. And there are a lot of great Easter eggs that I'm sure Rohit will talk about in his talk, so I won't give it away. But there are still a few more Easter eggs to be found related to future human exploration. I'll just leave it at that. So the part that I really want to focus on is the sampling and caching system. So as you know, this rover is going to go and collect several samples. So it has a suite of 43 tubes that we sent to the surface of Mars, as well as of those, 5 of them are witness tubes. And those witnesses are kind of like your negative control. If you were to, for example, take a sample from your backyard, and if you interrogate it and you say, there's an interesting feature here, but did it come from the collection device that I used to collect that sample from my backyard? So in order to make sure that it wasn't an artifact of your tube, of your collection device, you bring a negative control to compare, just to make sure that what you're seeing is a true signal. So that's why we have these 5 witness tubes. And the goal is to at least return at least 20 samples to collect and return back to Earth. So it is my personal favorite part of the entire mission, which is to collect, cache, and eventually return these samples. So as we collect these samples, several years ago, so all the way in the design phase, the scientists were concerned at first all of the tubes would be cached in the belly of the rover, and at which point at the end of the collection phase, it would be put on in a carousel onto the surface of Mars, and then a future rover would collect it. And there was a little bit of concern that, well, how if the rover died, is there a way to retrieve it? And just to ameliorate any concerns of possibly not having access to the sample if something happened to the rover, there was this depot caching strategy that was evolved to be the baseline path forward, which is, as you collect a certain amount of samples, you would deposit them on the surface of Mars, so you always have access to that group of samples on the Martian surface. And so you never really lose the ability to retrieve these tubes. And then in association with the European Space Agency, so we heard ESA being brought up earlier in the introduction, this collaboration shows that it takes a village, and the village, it's very important to loop in the international community. And even a lot of the instruments that are on the Mars 2020 rover are international payloads. And to continue with that theme, the European Space Agency and NASA are working together to have a series of spacecraft to collect and return these samples to Earth. So you can see in this cartoon here, here's Mars 2020 as a cartoon rover here, the Perseverance rover. As it collects samples and deposits them on the surface of Mars, in parallel, there's going to be a sample retrieving lander that's going to be launched to the surface of Mars. It's going to retrieve these tubes. Also, in parallel, there will be an orbiter waiting in orbit around Mars, such that once the tubes are collected and launched into Martian orbit, they can be captured by this satellite, and then returned on an Earth return vehicle back to Earth. And so, as you can see, this is a multi-mission and multi-agency effort. And it takes, again, a village for this to succeed. One thing that I want to also point out, there was an emphasis on STEAM also in the introduction talks. And I want to say all of these graphics, all of these animations, all of the thought that goes into designing this, the arts part, the A in the STEAM is also extremely important to be able to communicate this complex series of phases to the public, to each other. So it's very important. The A in the STEAM acronym is extremely important. So pivoting back to planetary protection, as you heard in the earlier part of the talk, is really stemmed from our desire to make sure we don't contaminate environments that we're exploring. And in the context of Mars exploration, as we send our spacecraft to Mars, all the way, we're not looking just at the rover, but all the way to the launch vehicle scale. We make sure that it's clean enough prior to launching, such that when it lands on the surface of Mars and it performs its operations, it can do it in a clean manner to limit the contamination of Mars. But as you saw from the last graphic, where we intend to bring the sample back, the goal is eventually, as we bring the tubes and the sealed container back to Earth, that we do it in a safe way to protect our own biosphere here on Earth, the Earth and the Moon, and to protect that biosphere and ensure that it's done in a safe way. So how do we do this is the next question. This is done in many ways, to include cleaning. Cleaning is actually fairly standard. I'm sure many of you through the global pandemic have been cleaning off your surfaces with isopropyl alcohol 70-30 mix. As you continue to do that in your home practice, just know you're doing the exact same thing that we do when we're building spacecraft hardware. In the upper left-hand corner, you can see I'm actually collecting a sample, but in the same manner, we wipe down spacecraft with IPA. We expose spacecraft to high temperature processes. This is a picture of the sample tube assembly and the DVT, the dispenser, the seal dispenser, volume assessment probe, and tube assembly cluster that was baked at a high temperature for 150 degrees Celsius for 29 hours. And these are certain ways that we keep the spacecraft clean, and especially our critical components are in fact sterilized. We do all of these practices. We touch the critical components with only autoclave sterilized components to just make sure these hardware are clean. But we also verify. We take samples throughout the entire build of the spacecraft, and just to make sure that we indeed maintain the cleanliness of these surfaces. So this is a picture here actually, I'm collecting this swab within the sampling and caching system volume, the adaptive caching assembly volume in the belly of the rover. And this was moments before the ejectable belly pan was installed for the last time on Earth. You can also see in the background here, this is the debris shield of the helicopter. So the actual flight helicopter is under this large debris shield it was already installed for the very last time. And now you see it was deployed already on the surface of Mars. If you notice here in these pictures and in your observation of the videos of the team building the spacecraft, we're always wearing bunny suits, these clean room garments where we're covered head to toe, because as you imagine, humans are the largest source of contamination and the largest threats of contamination to the spacecraft as we build this hardware. So bunny suits and face masks and gloves are ways that we keep the largest source of contamination separated from the spacecraft itself. And when we collect samples of the spacecraft, we're actually looking specifically, one of the key things that we're looking for is bacterial endospores. And these endospores are critical because they have the capability to form these seed-like structures that can stay dormant for millions of years. And when the right conditions arise, just like when you plant seeds in your garden, when you add sunlight and soil and nutrition, right? When you have the right conditions, it can germinate and grow. And these are the types of microorganisms that our planetary protection requirements are written around. So our maximum limits are in terms of spore limits. So as we take samples, we grow the samples in our lab. We identify the microorganisms that are present on these spacecraft samples. And then we archive them. We have an archive all the way leading back to Viking of microorganisms that were found on spacecraft. And as you can imagine from this method, it's somewhat limiting, right? Culturing takes a long time. Also, only about 0.1% of microbes can actually be cultured in the laboratory setting. So you can imagine that this is somewhat limiting. So in addition to that, one thing that we've been trying actually for several missions in the past, and we formalized it for Mars 2020, is we've also taken a separate set of samples and extracted the DNA. We've archived it for future technologies, because as you know, next generation sequencing, all of the sequencing capabilities just continue to evolve at leaps and bounds. So we take a set, we archive it for future technology development, and we take a set and we put it through high throughput sequencing, and we look and see what is specifically there. And we have, in fact, a passenger list of all possible microorganisms, not just bacterial, but fungal, archaeal, microbes, viral, that exist on the surface of the spacecraft. And what's amazing about this particular process is it's relatively fast compared to our normal culture-based method. And it also revolutionizes our ability to understand that ecosystem, the clean room ecosystem. Using these methods, we are actually found novel species that live in the clean room environment. We submit these sequences of everything that we find to public databases so that we eventually find links to other weird and crazy environments around the world. So not only are we looking to make sure we meet our requirements for planetary protection, but we're actually building upon the state of the knowledge in the field of microbial ecology. So as we collect these samples, just to give you a few rough numbers, we've taken over the course of the entire build of this mission, so starting around our first samples around November 2014, we've taken to July of 2020, we've taken 13,042 swabs, 3,521 wipes, 318 air samples, because you can imagine the air is a source of contamination, of fallout. And we've taken over 1,000 samples that we've interrogated using this genetic method, extracting the DNA and looking at the sequences. And when you compare us to the actual requirement, so as I mentioned earlier, our planetary protection requirement is in terms of bacterial endospores. We have a limit, we have actually two limits of 300,000. So everything that lands on the surface of Mars, because you can imagine here in this picture on the upper right-hand corner, the fairing that surrounds the entire aeroshell here, this fairing doesn't make it all the way to Mars. And nor does the crew stage. But of those items that do make it all the way, there's a maximum limit of 300,000 spores. And of all of the things that get launched, for example, this vehicle, which is a source of recontamination, of everything that is launched into space, there's a maximum limit of 500,000. And we met both requirements with a significant amount of margin. So we're actually quite excited and proud of all of the engineers that put their blood, sweat, and tears into making sure that not only there's a working set of hardware, but it was done in a clean way to meet our planetary protection goals. So as I'm sure you've all seen, on the 30th of July, we launched, in fact, milliseconds early. And on the 11th of February, 2021, we successfully landed on the surface of Mars. And there are a lot of exciting things to come. I'm sure you've also seen that the deployment of the helicopter already happened a few sols ago. And it also successfully at least completed a low speed spin test. And it's still pending a few more developments, but it will soon do its first powered flight on another planet, which is an incredible feat. You're looking at an environment with 1% of the atmosphere of what we have here on Earth. So they had to go through a lot of engineering feats to make sure it was light enough, that the rotors were fast enough, and it was 2,400 RPM, and to ensure that we had a successful powered flight. So we're all holding on and excited to see this milestone happen. Just to give you a little planetary protection connection, the helicopter itself, of course, was one of the many things that we sampled and ensured it was actually extremely clean. But it also carried a piece of the Wright brothers plane. So the first powered flight that happened on our planet, a piece of that, a relic of that airplane was actually attached to this helicopter. And we actually had to sterilize that piece of plane, of airplane material, before it was affixed to the helicopter. So we had to ensure every single piece of the spacecraft was clean enough to include the Wright brothers piece of airplane material. So the next thing that I'm extremely excited about, and I'm sure you all are as well, is the sampling and caching phase. And this is the part where the meat and potatoes come together. And I'm not going to say that the science begins, because the scientists have already begun their interrogation of the Martian surface. But this is the time where I'm excited that all the samples will be collected, cached, and we won't really know whether or not we did the best job possible until we bring these samples back to Earth. But it's my goal and the team's goal to make sure that we did the right job, that it's clean enough, and that we get to truly interrogate the surface of Mars and understand whether or not ancient microbial life even existed. So it's going to be a big deal. So with that, just my charge to everyone listening today is, as you consider designing your own spacecraft and exploring other environments, looking at how humans interact with those environments, my charge to you is to keep planetary protection in mind and to be good custodians of our universe and to explore responsibly. Thank you so much.
Thank you, Dr. Cooper. And if all of our webinar participants can join me in saying thank you very much. It's a fantastic presentation. I'm going to kick us off with our first question, and then just want to remind all of the webinar participants that you can, if you have a question for Dr. Cooper, please put it into the Q&A feature. It should be at the bottom of your screen in Zoom, and then we will have an opportunity to read out your question to Dr. Cooper and get it answered. So first question for you today, what are you most excited for this next mission headed to Europa? So I understand that you're also beginning to think ahead about some of the planetary protection considerations for this Europa lander mission. Can you tell us a little bit about that?
Exactly. Yeah, that's a fantastic question. Yep. So currently I'm the planetary protection lead of the Europa lander mission. And right now we're working with NASA headquarters to develop the requirements for this mission. The key goal, and my key goal, is to continue to revolutionize the planetary protection field, to not only use this traditional culture-based way of looking at spores and how many spores exist, but to use metagenomics and to use all omics to understand what specific types of microbes exist on the surface of that spacecraft, and to limit those microbes that may find it easier to survive in, for example, high radiation environments. As you get to the Jovian system, right, you have a completely different environment than if you're sending something to Mars. So looking for example, the Deinococcus radiodurans and all of the other spore formers that may have a high threshold tolerance to radiation and desiccation. These are the things that we're going to be looking for in developing the requirements to the Europa lander.
Interesting. That's fascinating. I know many of us would love to stay tuned with your work in this regard. It's so exciting to be thinking about this next destination in the near solar system as well. Back to your amazing work on Mars and planning ahead for the Mars missions and the Mars rover. We are all hoping that in the next few years, maybe a decade, we don't know exactly when, that we'll have this Moon to Mars human mission, right? So we'll be building on what we're learning from the Moon now. We'll be sending humans to the surface of Mars. As soon as we have humans there, to your point about bunny suits, we'll be shedding like crazy all of the different aspects of the microbes that live within us. What would you like to see as this balance between letting humans be on the surface of Mars and begin to explore with their bodies shedding, as we will do, and then also protecting certain areas that might still be really important for pristine astrobiology investigations, assuming that we haven't finished all of the astrobiology that we want to investigate by the time of the first human mission? Can you maybe talk to us a little bit about how you think about that balance once we come to
Yeah.
the human domain.
Yeah, exactly. Yeah, as a human, right? I long for human eyes to be on the surface of Mars and to see and explore. But of course, with the planetary protection side, clearly there's that limitation. However, the whole fundamental basis of where these planetary protection requirements come from earlier conversations, back with Coleman, with Carl Sagan and Coleman, and they're talking about exploration and how we can get these high astrobiological value samples and do this exploration before the cesspools of microbes, which AKA humans, completely change the landscape. And I think there's a way as we transition from a pristine environment to a human inhabited environment to maybe even have these national park like regions of Mars. I mean, of course, it's going to have to take a lot of consultation with folks that understand the dynamics and the spread of how these microbes could possibly work its way to those areas in an airborne form. So it may not be able to be held pristine for too long, but you can think of maybe national park type regions within Mars that will allow us to continue to explore certain areas while still keeping it relatively untouched. But yeah, the landscape will definitely change as humans go onto the surface. And that's why I urge you all, I'm sure there are people listening today that are going to be part of the team designing these future missions, designing the spacesuits, designing how the airlocks work. And if there's a way that you can kind of keep things contained, keep our contaminated air contained to the hub, those are things that seeds that I want to plant in everyone's minds today.
That's a fantastic point. I know we do have several space architects on the webinar this morning based on who I see have tuned in. So this is a fantastic call to action for those folks who are going to be thinking about the human infrastructures. Are there ways to be responsible in the design from the ground up and answer some of what Dr. Cooper is calling on us to think about? That's really interesting. All right, I believe we have a few questions coming in from the webinar, so I'm going to pull this up now and we'll go through as many of these as we do have time for. One question from Tamara Alvarez. What do you think about PPPs on the moon? For example, the tardigrades, and how to protect inorganic samples as well?
Yeah, that's a great question, and it definitely caused a big kerfluffle with the tardigrades that were secret passengers to the moon. Yeah, it's important, and we actually have limits. I didn't talk about that in this talk today, but for the Mars 2020 mission, we actually had limits on inorganics as well, organic, inorganic, and biological contamination limits. So it has been and continues to be a concern for us to make sure that the limits, including on inorganics, are in parallel with actual old Martian meteorites. We use an SNC, I think Shergadi, Nakla, I don't recall the full expansion of that, but an SNC meteorite. We use that inorganic profile as our way of limiting the total contamination so that we can look at our samples and make sure we don't have extra contamination that we introduce to it. So great point, great question. And yeah, that is going to continue to be a concern in organics, and hopefully limiting also organic, inorganic life as well.
Interesting, thank you. We have a question coming in from Dr. Sunanda Sharma, who is a member of our Space Exploration Initiative as well, and will be our moderator for the later Life in Space panel today. Sunanda writes, turning to Earth, Dr. Cooper, do you think there are places on Earth that are not contaminated yet, or could be sites for us to practice how to study the results of potential contamination?
Yeah, that's a fantastic question. And there are actually several places within the Earth that I think are really ripe for the practice. I mean, not only in Antarctica, there are all of these subglacial lakes that you can tap into and find a way to do it in a responsible way without having too large of a negative consequence because you're only introducing Earth life to an Earth environment. But there were places like Lake Vostok. I think that is now no longer pristine. I think it's been tapped into already. But there should be other environments on Earth, and yeah, I encourage you to find those environments and test this out and have these lessons learned, so that when we go to other bodies like Europa, we can really do it in a responsible way. Yeah, that's a fantastic point. The Earth is a great test bed.
Very interesting. We have another question from Jipeng Liang. Where will the nuclear waste from the rover go after the mission? Now, I know that this is a question that many people at NASA will also be thinking about and looking at, but if you have anything that you'd like to weigh in here to share, I think it would be interesting to hear if you have thought about this in the context of planetary protection.
Yeah, well, in the context of planetary protection, so we're looking at the microbial contamination, right? And not necessarily contamination by any waste per se. But as far as but for the MMRTG, the thing that planetary protection engineers love about this nuclear source of power. So just for those who may not know, there's an MMRTG, a multi-mission radioisotope thermoelectric generator, which we take the heat from the decay of this nuclear source and turn it into electricity to power the rover. And so that process is actually at quite high temperatures, and it's at self-sterilization temperatures. Actually, it's over 200 degrees Celsius in the core of this reactor. But over time, the decay is going to wear out. I believe it's on the order of 7 to 14 years. I believe it's going to kind of teeter away, and it's just going to stay on the rear of the rover. So there's not really going to be a collection. It's not going to be buried anywhere. It's going to be above ground, and it will be just staying with the rover the entire time.
Interesting. We have another question coming in from Dr. Martin Elvis, who is a professor here in Cambridge at Harvard at the Center for Astrophysics. And he writes in, how do you decide the limit of microbes allowed? Why is it 10 to the 5th?
Yeah, that's a great question. That's a fundamental question, right? So for Mars missions, actually for all missions, right? There was a conversation that happened a few decades ago with Carl Sagan, among many people, that tried to essentially limit the contamination to other worlds to the probability of 10 to the -4. So when we are going to Europa, it's the same number, right? 10 to the -4. We have to make sure that the probability of inadvertent contamination is at or below that number, that value. And it's similar with the Mars missions. It's 10 to the -4, but it was translated into, okay, if we have X amount of missions over X amount of years, an exploration period, what would that look like in terms of biological limits? And that's why it's 10 to the 5 for every single mission. So it was a conversation that happened many moons ago, where these limits were agreed upon. But with that said, has been a lot of evolution as far as how we really implement that and how we enhance our requirements so that it really captures the science of what we're doing on that mission, and make sure that we do the right thing first and foremost, and not just meet this requirement. And that's why for the Mars 2020 mission, we're actually far cleaner than the requirement, not because we could be, but because the science actually dictated that level of cleanliness.
That's an interesting response. And I wonder, do you see, because this dialogue started with Carl Sagan years ago, and then has evolved, and you guys have been doing the best across the planetary protection community to stay within these limits and these targets. Do you see that evolving over the course of time? So if you were to say develop the next generation of recommendations for missions that would go on to Europa and beyond, are you likely to, for this flight heritage concept that we have in the space, because it's been done like this before for standards keeping, would you stick to it, or do you see the community updating these limits and taking a new approach?
Yeah, I definitely see the community updating the requirements. And the beauty of planetary protection, even though it seems like it's kind of set in its ways, it's really not. And there have already been changes to the international policy. So NASA takes its rules from an international policy that was signed by several countries that allow the whole world, right, to abide by these standards. And so that has already changed. There have been changes in the text related to Venus. Venus used to be categorized as a place where we would never find life. And now with the evolution of understanding, something may live in the upper atmosphere. So the rules changed toward Venus. Similarly, there are conversations about human exploration and how that ties into planetary protection. So there is constantly a slow evolution within the planetary protection field. So I can definitely see that changing over time.
That makes a lot of sense. And it's great to hear, of course, that it's responsive to the increased knowledge that the scientific community is bringing to the question. And yes, those phosphines, all that interesting research coming out of what may or may not be present in the Venus atmosphere. That's really
exactly.
Yeah. I think we'll go with, maybe we just had an extra one come on. The next question I have queued up for you is maybe a more of a meta question about how you see collaboration in the space industry. You mentioned in your talk the importance of international collaboration, the integration with ESA for the Mars sample return mission. We have a question here that's touching on, for international citizens who have maybe done some amazing work in genomic sequencing for astrobiology or other ways in which they would love to contribute to the planetary protection field. What are ways that they can get involved? Because of course there's some pathways for international citizens at JPL, but it can also be difficult within, if you're the government ecosystem. Do you have thoughts on how international folks who might be on the call today can really contribute to your field?
Yes, in fact, we have several collaborators from the UK, from all around the world. So it's not a limiting factor that you're a member of the international community, especially for the reason why we have a lot of restrictions within NASA is there's a lot of the secret sauce, right? The designs that can't be shared, a lot of those particulars. But when it comes to science, as long as it's not tagged to particular regions of the spacecraft, all of that that science data is shareable. And so it just takes, it's a matter of finding a connection within NASA and signing the right agreements. But it's definitely doable to have collaborations within NASA in this international context. For astrobiology, looking at this data, looking at the omics, doing all of these collaborations. Yes, it is possible.
Thank you for sharing that pathway. I think that is always really important to remind people that within academia and within the amazing work happening at JPL, you can reach out to the scientists that are leading those endeavors and begin a dialogue and a relationship about sharing data. And NASA does an exceptional job and really leads in this domain of making data accessible and doing open access data. Of course, the formatting and the working and the details of getting into that data can sometimes be tricky if you're not the original data owner, but NASA does a really good job of making data open access for scientific investigations.
Yep.
And with that, one final question for you today, Dr. Cooper. We have someone who's writing in to ask, somewhat similar to Sunanda's question from before, but a little bit different. Is there a good example or a lesson that we've had on Earth for planetary protection? So we're taking all these ideas to Mars and exoplanets and such, but it was interesting for this person, they write, to hear about the national park comparison. Mm-hmm. How can scientists and policymakers working together and bringing knowledge back from planetary protection on other planetary bodies think about earthbound eco-protection?
Yeah, we see this on a daily basis when it comes to, I'm sure, I don't know if anyone here has tried to bring wood to Hawaii, right? It is more on a agricultural scale when you look on the scale of Earth. When you're bringing fruits, right? You can't bring fruits internationally because they harbor some form of life, either bugs, macroscopic life, or even microscopic life. And that desire to try to contain that and make sure there's not the strong ecological impact is what is manifested in a lot of these agricultural rules when we travel. So yeah, there are definitely examples on Earth every day of a smaller scale planetary protection, and ways that we can kind of improve the transit of microbes as they move about.
Thank you so much, Dr. Cooper. It's been absolutely a delight to have you. Thank you so much for kicking off our first session here for Beyond the Cradle. If there are any final words you'd like to leave with the audience, this is your moment. And then shortly after, we'll be transitioning to the lightning talks.
Yeah, I'd just like to reiterate my charge as you think about exploring and making your designs, just keep planetary protection in mind and explore responsibly.
Thank you so much. Thank you, Dr. Cooper.
Thank you.